Welcome everyone to a series of lectures that I'm going to introduce machine learning tools, specifically non-neural network-based machine learning tools, in order for us to learn how people have been using machine learning for actually quite a long time, well before we saw the deep neural nets take over in many application fields. So what we want to talk about are some of the ideas that we might have available to us, and specifically learning supervised versus unsupervised learning techniques. And I want to walk through sort of these strategies that we might have, and they are very much like they sound. Supervised simply means that you actually are going to label your data, and there's a mathematical way to represent this. And unsupervised is where you actually bring in data and you're actually looking for patterns in the data that you don't necessarily know is there potentially, and so you're not going to provide labels. The machine learning tools themselves are going to have to find the patterns out of that data. And so we want to talk about some of the dominant techniques for both supervised and unsupervised learning. And what we're going to walk through is a series here and to show you these specifically in the context when we're not using neural networks. Okay, so let's go ahead and talk about these here. All right, so some of the goals that we might have for this, and these are traditional ones, so it's not everything. In fact, you'll see a lot of the examples we do. We don't necessarily do what are just called clustering and classification, but clustering and classification typically represents one of the big efforts we might try for, which is I want to take data and I want to look for things that are alike. So for instance, if I was looking at pictures or images and I had dogs and cats, I may want to look for things that look like dogs and things look like cats. So that would be a clustering exercise. What we're doing here is thinking about taking the data and putting it in appropriate bins for us to sort of start to doing analysis with. Classification is related to clustering because once I have these clusters, I may want to bring a new data set to you or new pieces of data to you, and I want you to take that data and classify it into the clusters that we might have available to us. So for instance, if they are pictures of dogs and cats and horses, what the classification would do, it would take a new image of one of these animals and give it a label. Is this a dog or a cat or a horse? So clustering and classification tends to be one of the very traditional things that you would be doing with machine learning techniques in general. Okay, so we're going to kind of look at what we might do with this. So first of all, just to formalize that a little bit more, I want to just take and distinguish what we mean by supervised and unsupervised learning. So what I'm giving you over here is two pictures. In the left picture here, actually it's your right picture, this one here. Here's a bunch of data points, let's say. Now they're all gray because I don't know what they are. I haven't given you any labels. So your objective in something like this with this data is to bring back labels. So it's unsupervised, and the idea here is that an unsupervised machine learning algorithm will look for patterns in the data. And what I've done here to generate this data here in this cluster was generated from some Gaussian random distribution, and this is from a different Gaussian random distribution. And of course, you can see here, they sort of belong in two separate clusters. I don't know this necessarily, and so the idea is from taking that data, how can I take that data and have it automatically identify this cluster from this one right here? So that's the goal, let's say, of unsupervised learning. Our further picture over here is supervised learning. So what I'm giving you again is a bunch of data, and let's say the gray dots are things that I don't know, but I'm also giving you both the magenta and green balls. In other words, I label them. The data that's here is magenta, I'm actually labeling it as magenta, and the label that's green, I'm labeling as green. So now your goal is to say, tell me what these gray balls, these new data that I have are, given the fact that The magenta is what I'm going to call the magenta balls, and the green are the green balls. So here, the supervised learning task, I am guiding the process. I'm labeling data for you in order for you then to follow up with a classification task or a clustering task. Supervised learning is always more successful than unsupervised because you are providing expert knowledge, you're providing the labels, and so the machine learning knows what it's looking for. Unsupervised is, in many ways, often what we do when we don't know much about our data. We're actually looking for patterns in the data, and what we're hoping is the unsupervised learning algorithm can actually extract things for me in order for me to understand the data. So there's a big difference between these two. And you're always going to be, there's almost 100% guarantee that you're going to be more successful doing supervised learning than unsupervised learning. But of course, supervised learning requires you then to produce a training data set with labels, which is, that's part of what the supervised learning algorithm is all about. So this is kind of like just a sketch, a cartoon of what we might be thinking about. And we'll kind of show some of these methods that we might do for both of these things, unsupervised and supervised, and some of the dominant techniques that have been developed over decades that were not neural network based. Later, we will follow up with neural network techniques on how we might be able to do the same kind of tasks here, especially for supervised learning for neural networks. Okay, so, and again, this is just another figure here, and what I'm showing you in this figure, so in this figure here, it's pretty easy with your naked eye to see, oh, there's two distinct clusters, so labeling the data should be pretty easy. But what happens if I just move these two clusters closer together? And I think part of the reason I want to show this is it shows you how difficult unsupervised and supervised learning can be. Because this is not a hard problem in many ways. It's two Gaussian distributions. It's actually the same data set here where I just took the center of these two data sets and of these two clusters, moved them together. And so now I have, in an unsupervised framework, I have this data here where it's very difficult for me to distinguish which came from which. And even if I have labels, look how the magenta and green overlap. So for me to sort of make a classification decision based upon where the data is, it's very difficult, especially as I'm in this region here where the magenta and the green are completely overlapping. And then so if I give you a gray ball there and ask the question, is this gray ball part of the magenta cluster or the green cluster? It's really difficult to do in this case unless I'm away from where that green is right there. So these are the challenges that we have with data. Often, data is noisy, it's corrupt, it's not clearly separable in some feature space, and then you have this situation here, which makes it very challenging. And of course, you're always hoping for what happens up here, which is, just with your naked eye, you have a pretty good idea of where the data belongs in terms of the clusters. So these are just practicalities we have to think about, which make data science incredibly difficult at times, depending upon the data set. And depending on how clean the data is, how good the labels are, and so your success is going to depend quite a bit on that. So for instance, let me just give you an example. If you were to try to distinguish between horses and dogs versus distinguishing between a dog and a spider, a dog and a spider are very easy to tell the difference, but maybe from a distance, even a dog and a horse might be a little bit harder to write an algorithm to distinguish between them. And so these are the kind of things that show up in a feature space. In a feature space for dogs and horses, they both have 4 legs, they both have a long neck and a long snout. But sometimes that may be hard for a machine learning tool to actually identify the difference. Whereas for a spider, it just has such a different feature space, many legs, completely different body shape. So machine learning should be able to presumably pick up those differences very nicely. Okay, so let's start laying down some mathematical foundations of this. This is very important because all of this is framed around mathematics. And so I want to start thinking about how we construct the supervised and the unsupervised learning problem in terms of a formal mathematical structure. So first of all, I want to introduce the domain. So I'm going to make some n-dimensional space, D, this is sort of the domain of our data. So this is all where the data can be collected from lives in some domain D. So one way to think about this, if I think about pictures of dogs or cats, D represents all possible dog and cat pictures that might be available to me. However, I don't have an infinite resource of data. What I have is a finite collection. So the data I collect from this domain, let's call that D prime. So D prime is my sampling of the data domain. Okay? So I might have 1,000 dog pictures. So 1,000 is my D prime, and my hope is that 1,000 pictures I have is a good representation of the actual data, which is D, right? The domain of all possible data that would be from that. Now, this is a really important concept, and specifically, what is the gap between D prime and D? You have a finite collection of data, and the question is, how well does it represent all of D, right? And a lot of machine learning challenges and failures stem from this gap between D prime and D. If you have a new data set that somehow is in the convex hull of D prime, in other words, I give you a new picture that sort of lives in an interpolated regime of D prime, then you're probably going to do okay with your machine learning. But if I give you a new picture outside of D prime, so I have to extrapolate out there, it's still in D, that's often when machine learning will fail. So it's very important you understand immediately when you have a machine learning package that you already have this issue of your data does not represent all possibilities. Your data represents a finite set of possibilities, okay? And there is a gap between your data collection and the full truth. So this is how we represent this. And one of the success stories of machine learning has been, I simply collect so much data. So in other words, I'm trying to make D prime as big as possible, that D prime have collected so much data that I basically spanned almost all of D. Or another way to say it, I've collected so much data that the gap between D prime and D just shrinks and is almost zero. Okay, so that is a tried and true method for making machine learning work. Collect more data, because then you've seen more and more of all the possibilities that are available to you. Okay, so this is the infrastructure of where we collect the data and how we span it. And so now we can start mathematically formulating the problem, for instance, of unsupervised learning. And here's how it's structured. So the input is some data. So let's call it X of J. These are each data piece. And of course, they live in some n-dimensional space. And J, I've collected here, I have M samples of data. So this is my input data that I give to you. And in an unsupervised way, I don't know what this data is. Remember, I have no labels for this data. I just say, here's some data. And what I want you to do in unsupervised learning is to pull out structure and patterns that are somehow meaningful. In other words, what I want to actually happen in unsupervised learning is that I give you the input data, and I want you to give me the output is going to be a set of labels for that data. Let's call the labels Y of J. So the Y of J could be, for instance, plus or minus 1. So for instance, maybe if I have pictures of dogs, pictures of cats, I give you a bunch of pictures of dogs and cats, and what I want you to do is produce labels. So from all that data, find for me things that are plus 1, let's call those dogs, and minus 1s that are cats, okay? You're providing the labels yourselves. The label doesn't have to be a numeric value. The label can be a string, can be dog, cat. It could be that the dog is a plus 1, cat is a minus 1. The point is, you're actually asking this to pull out labels for you. Very important. The number of labels, you actually have to pick that. And this is one of the challenges of unsupervised learning, is I don't know how many objects are sitting in my data set. So in all the dominant methods that I'm going to present on unsupervised learning, it is your task to decide, do I have 2 things in there, 3 things in there? Often then, in other words, a way to say this is, how many clusters do I believe are in my data? And so this is very challenging because the dominant methods force you to prescribe the number of clusters up front that you're looking for. And so oftentimes people do this through trial and error, cross-validation, and to try to get the best number of clusters that represent the data. Okay? And again, this is a very big difference between unsupervised and supervised, because in unsupervised, you don't know, but in supervised, you actually have labels. You can say, here are the number of distinct clusters that I have. Here are their labels. And in unsupervised, you don't have that. Okay. So this is the mathematical framework for unsupervised learning. You take data, that's the input. The output is a label. And the number of labels is something that you specify. All right. Supervised learning is different. Supervised learning means that I actually have labels to give to you. So I already know what I'm sort of looking at. So the input now is not only the data, and still same amount of data, M data points, let's say, and M is often very large, but I also give you for each data point a label. So I'm labeling that data for you. So for instance, if it is pictures of dogs and cats, I give you, here's a dog picture, I label it as a dog. So for instance here, the labels might be plus or minus 1, but again, it could be a string. So maybe the +1 is a dog, -1 is a cat. So I give you a bunch of dog-cat pictures, and I give you a plus or -1 for each picture. So I've told you, here's what a dog looks like, here's what a cat looks like, okay? Now the output is what you're gonna do is, now that I've given you this, I can give you now either new data, new pictures of dogs and cats, or I can even just rerun my algorithm. Once I've learned a model, I can rerun the data through and see what the labels come out to be. Okay, so I'm trying to learn a classifier. So in other words, I bring in a new piece of data and the output is a label. So I'm gonna classify each input into an output. But remember, you get to build this classifier by basically the fact that you train the model. So you're actually saying, I'm giving you labels. That gives you a guide to what I'm actually looking for. I don't have to even pick the number of clusters or number of classifiers because it's all in the labels, okay? And so once I have that, I provide an output, and the output labels are what I get out of here. And also now this model, once you've trained it, can just be used generically, let's say, in a reduction to practice algorithm where you deploy it in real life, where maybe you have a computer vision algorithm which is trying to identify pictures of different animals or labeling different natural scenes, where you say, look, well, here's a natural scene. I'm going to label this as a mountain. This is a road. This is a car. All those come from labeling procedures that you would have done here with your input data. So that's the key difference. Let me go back real quick. Remember, unsupervised, no labels provided. You don't even know how many labels there are, but the goal is still to produce output labels. So this is a much harder task than if you go to supervised. You actually have labels in the training process, okay? So by the way, this outline of unsupervised, or here specifically supervised learning, is standard for machine learning. And this kind of outline for supervised learning holds not only for non-neural network-based methods, but also for neural net-based methods, which we will consider in later lectures. Okay, so let's go ahead and get detailed about this, and I can actually walk through a little bit of how this works in practice. So there is an iris data set that is sort of fairly commonly used, and what it is essentially 3 different types of irises, and each of the irises have characteristics. So here's essentially the feature space or the vector characterizing each. There is the sepal length, sepal width, petal length, petal width. So there's 4 parameters that are measured on the iris. And for each of these, if we were doing a supervised algorithm, I would measure it and I would tell you what kind of iris it is. There's 3 different types of irises that are in this data set: a setosa, versicolor, virginica. So in other words, what I've given you here is a clear example of a supervised learning algorithm in which I've given you the data, which is the characteristics of each, and the label, which is the type of iris it is. Okay, so for each flower I might have of this iris data set, you would basically compute these or calculate these by measurement, and then you would have the label because you can actually see the flower, and you would say, okay, this is my setosa, I take the measurements, and that's one of my data points with a label. Okay, so that starts setting up an architecture whereby if I took a new flower and I just basically gave you these measurements, I want you to say, here's the measurements of my flower. What should I call it? What kind of iris is it? Okay, so this is the idea here of this task, is to take these measurements and give it a label. And let me show you what this data set actually looks like. And again, you can see the power of supervised learning here, because what I've plotted, there's of course 4 characteristics, and I've only plotted 3 here because that's all I can plot in 3 dimensions. And so these are just 3 of the characteristics. And what I've given you here in these different colored balls is, for instance, all the setosa sit here. The greens are the versicolors, the blues are the virginica. And you can already see with your naked eye, there's some clustering that happens. Now, when you look at this, and if I were to take away all the colors, you would clearly see that, okay, this cluster here, you might be able to identify with your naked eye that it's a separate cluster. So even if I did unsupervised learning, you might be able to pull this one out and say, this seems to be different than this over here. And by the way, here it would be hard to decide, are these 2 separate clusters or 1? So it'd be very difficult from an unsupervised learning point of view to decide if it's versicolor or virginica, but clearly the setosa seems to be separate. But when I've provided labels to you, you can see it all, and you can already see that, oh, the greens are down here, blues up here. Even though they kind of blend into each other, there clearly seems to be a line between them. And I would only know this if I had the labeled data. And so having the supervised version of this, where you provide the labels, allows us to come after this problem and solve it from a machine learning point of view. And of course, we're going to go into these different methods as we go through, both in terms of coding and in terms of methodologies, because there's quite a diversity of methods that are given to us for doing supervised and unsupervised learning. Okay, let's take a different data set, or by the way, let's just dig down on the data set that's actually there. So let's go back to here. So remember, sorry, here we go. If I go back to this picture, here's the feature space. Remember, I had, these are the features. Here are the labels. So now when I come to this, here are the pictures here, and you see a finite number of data points here. And so let's go ahead and actually look at what these are. So in fact, what you have here actually very specifically is the following. The data set is 150 iris samples. Okay? There's 50 of each type of iris, so it's balanced. This is very important because often we have to also talk about unbalanced data. So if you try to build a model, let's say, where I had in here, let's say I had 150 iris samples, but I had, 140 setosas, only 10 versicolor and 10 virginica, then what would I label data? Well, why not just call them all setosas? Because my accuracy would be, in the 90-some percentage. Not because I did a great job in classifying, it's just the data is unbalanced. It means that to get it right, I just can guess setosa because almost all of them are setosas. So here what you're seeing is a balanced data set, 50 of each, okay? And that's the domain D prime. So remember, D prime is my data. The actual D, the real world, is all these flowers, right? There's a lot more than 150 of these flowers, right? So this is just representing for you D prime versus D. Now the hope is your D prime, your 150 samples that you have, or 50 of each, are good representatives of that specific iris type. Otherwise, you're not going to do a good job in representing the whole world, which is all of the irises that you might come across of these three varieties. Okay? So this is kind of your gap between D prime and D is I have 150 and D is the entire rest of the world. Okay? Let's go to another data set we might want to look at. And I'm going to take here, I'm going to show you some images where we can do a classification. And I've kept mentioning this, but looking at the difference between dogs and cats, right? So in other words, how do I start thinking about classifying the difference between them? So I'm going to take some images. They're going to be 64 by 64 pixels. Okay, so the feature space is pixel space. And 64 by 64 gives me 4,096 pixels total. So in some sense, 4,096 is sort of in some, the state space of my data, right? That's the R of n, where n is now 4,096. So I'm going to take these images of dogs and cats, and what I want to produce is, or in the supervised method, I'm giving it labels. And for instance, the labels here, they can be a string, dog, cat, or I can turn them into numeric values, 1, -1. So in addition to giving you a picture of a dog or a cat, I'm going to give you the label, plus or minus 1, so that you know what a dog and a cat is. So in the data set we're going to look at, there's actually, the D prime is 160 images, okay? So 160 samples, 80 dogs, 80 cats. That's D prime. The real world is all dogs and cats, okay? You just have to go to one dog park, like in Seattle here, and you walk around and you can get a lot more than 160 dogs just within a couple hours sitting in that dog park. So already 160 images is a very small sample compared to the universe of dogs and the universe of cats, okay? And so, but again, we're just kind of demonstrating a few things. One is, what does the data look like? What's the feature space or the vector I'm putting in, which is pixel space? What is the label, plus or minus 1? My D prime is 160 images versus D being the entire world of dogs and cats. All right, so let me actually show you some of the pictures here of the dog and cat. So if I take these dog and cat pictures, and if I look at them in a low rank subspace, which is gotten for me from singular value decomposition, and this is something we've covered in the linear algebra section, then if I look in the dominant principal component directions, or SVD directions, then here what you're seeing here is labeled data of the dogs and cats on the raw images, versus if I take that data and I do a wavelet transform, and all the wavelet transform does is it takes an image and it highlights the edges, so I would look at dogs and cats and their edge features, then what I have here is this classification. And you can already see these two balls of data in either place. This is just trying to demonstrate something here, which is the dogs and cats are reasonably close to each other because they have a lot of the same features if you look at their faces, which is it's a face, it's got eyes and mouth and ears and a nose. So they share a great deal of features. And of course, some of the higher components start to highlight some of the differences between the features. And this is why you see that the purples are sort of on one side, the green on the other, but they do have a lot of overlap between them in both of these modalities of looking at the clusters. So the best you might be able to do is sort of draw a line between these purple and green dots, which we will learn how to do through this machine learning methodologies. Okay, so this is, that's the intro overview. So the goal of this was to just introduce this concept between supervised and unsupervised learning, and just to highlight the fact that what you're doing in these methods is providing back a label, right? If you're unsupervised, you're going to give me data if you're an unsupervised, and your goal with that data is to say, label the data for me. I have to pick how many labels I want. So unsupervised is much more difficult to do because you don't even know necessarily how many labels you might have. And so this is, unsupervised learning is for really starting to extract features from your data and start to learn something there. However, oftentimes we actually have a lot of information about our data, and we can provide labels. And in supervised learning, we can provide those labels, and we can provide a distinct number of labels for all of our data. And so what I've shown here, right, is there's an entire mathematical architecture that allows us to formulate this thing in a very precise way, so that when we build algorithms, we can actually start to mathematically go after the key component, which is, in some sense, accuracy of labels in what we're going to be doing. Okay, so what will follow now are methodologies in both supervised and unsupervised learning for us to both consider in terms of building models, but also in terms of code base and how we would implement them in Python.